Introduction to Solutions and Aqueous Reactions, Acid-Base and Redox Titrations. In this tutorial, we will be looking at acid-base titration terminology, equivalence point, endpoint, and indicators, basics of acid-base titration, along with some worked examples, of course, precipitation and redox reaction titrations, along with more worked examples. A titration is a laboratory procedure based on acid-base neutralization and stoichiometry. In a titration, a substance in a solution of known concentration, otherwise known as molarity, which we represent with a capital M, is reacted with another substance in a solution of unknown concentration or unknown molarity. The solution of known concentration is referred to as the standard solution, sometimes known as the titrant, and is dispensed from a burette tube. The solution of unknown concentration is referred to as the analyte and is typically contained in an Erlenmeyer flask. So this is a common setup over on the side here. We have your burette with our standard solution, and then we see our Erlenmeyer flask with our analyte. So the standard solution will have our known concentration. That is what we'll see in the burette. And in the Erlenmeyer flask, the analyte, again, will have our unknown concentration, what we are solving for. The point in the titration where the number of moles of hydroxide ions, typically present in the standard solution, again, the titrant, equals the number of moles of hydrogen ions initially present in the analyte is known as the equivalence point or the stoichiometric point. Now, what do we mean by equivalence? We see the number of moles should equal each other, but how do we know this? Well, we go back to our good friend, the molarity formula. So molarity is equal to moles over liters. I'm going to do that really quick on both sides as a reference point. And then I'm going to take this piece of information right here, and it says 0.05 liters of 0.1 molar HCl. So let's make this the acid side. A is for acid. So molarity is 0.1 molar is equal to moles, and this is our acid, so we'll say moles of H plus 1 over our volume, which is 0.05 liters, right? And then we cross multiply these and it's all good in the world. And when we cross multiply them, we find that we have 0.005 moles of H plus 1. Now let's do the other side, our base side. So this is going to be B is for base. So this says is titrated with 0.1 molar NaOH. All right, well, we have the molarity. So 0.1 molar hydroxide ions, because we really actually don't care about the Na. And we're going to solve for moles all over liters. And you might say, well, where are you going to find the liters? Well, I'm going to look at my graph, of course. And I can see that this is labeled at the equivalence point where we have this really straight up and down line right here. And that is happening at 0.05 liters. So we will multiply those two numbers together, and when we do that, we get 0.005 moles of hydroxide ions. So the takeaway here is the equivalence point literally means equivalent, like equivalent number of moles. Moles of hydrogen ions will equal moles of hydroxide ions. And we'll get more into these graphs later on in the year when we talk about acid-base equilibrium. But for right now, that's what we mean by equivalence point. Equal number of moles of hydrogen ions and hydroxide ions. The endpoint of a titration comes just after the equivalence point. The endpoint represents the end of the titration reaction and is marked by a change in color of an indicator. An indicator is a chemical substance, usually a weak acid or base, or a mix of them, whose color depends on the acidity or basicity of the solution. The endpoint and the equivalence point can occur at the same time if the pH of the titrant corresponds to the pH of the equivalent point. And again, we'll do this more in lab, but can they occur at the same time? Sure they can. Or the endpoint might come right after the equivalence point. It depends on the situation. So we can look at this graphic over here and we can see where the color change happens for phenolphthalein and where the color change happens for the indicator methyl orange. So in this situation, we can see that the equivalence point is just at the very beginning of this color change, which is marked as the endpoint. Noting the ratio of hydrogen ions and hydroxide ions from the chemical formulas of the acid-base species involved in the neutralization, the following relationship can be used to determine an unknown concentration or volume. So this is a formula you should be very familiar with. MAVA is equal to MBVB. You should have seen this in Regents chemistry already and have had some experience using it. So let's look at our example. Determine the volume, so we're looking for a volume here, of a 1.00 mole per liter NaOH solution. Now, before I get even any farther, I'm sure you might be looking at me like, what the heck is that? Well, that's just another way of saying molarity, because we know that molarity is equal to moles over 1 liter. And this L on the bottom can be represented as moles times 1 over liters, which is the same thing as moles as the reciprocal L minus 1. So don't get distracted by that. I took the time to explain it. So again, starting from the top, determine the volume of a 1 molar NaOH solution required to completely neutralize 25 milliliters of a 2 molar HCl solution. So the first thing that I am always going to do is write my formula. MAVA is equal to MBVB. And the thing that I want you to notice here is that the ratio of the hydrogen and hydroxide ions is 1:1. So 1 OH, no subscripts, no brackets, no nothing, 1 hydrogen. So I want you to keep that in mind. This is something you absolutely need to pay attention to when you recognize you're dealing with a neutralization reaction and you're looking at ratio to hydrogen to hydroxide. So it's 1:1. Good times. So we're determining the volume of the base, all right? And they tell us that the molarity is 1. So molarity is 1 molar. We are solving for VB, volume of the base, and then we have 25 milliliters. Of course, we're going to turn that over into liters because that's just the right thing to do. So the volume of the acid is 0.025 liters. And the molarity of my acid is 2 molar. 2 molar. And then if I solve for the volume of my base is going to be 0.0500 liters. And if we convert that into milliliters, we know that is going to be 50.0 milliliters as our final answer. Some neutralization reactions involve polyprotic acid. Remember, poly means many and protic means proton, so we relate that back to acids, which can yield more than 1 mole of hydrogen ions in solutions. Therefore, the ratio of hydrogen ion and hydroxide ions may not be 1:1. As a result, the MAVA is equal to MBVB relationship must be adjusted based on the given chemical species. So common polyprotic acids, sulfuric acids, H2SO4, ionizable hydrogens is 2, so we call it diprotic, 2 protons. Same thing with sulfurous acid, H2SO3, 2 hydrogen ions, diprotic. Phosphoric acid, doing something a little different here, H3PO4, 3 hydrogens, so ionizable hydrogens, the possibility of, are 3, so we call it triprotic. And then bringing back carbonic acid, H2CO3, ionizable hydrogens, 2, therefore diprotic. So those are some common polyprotic acids. Let's look at an example. Determine the molarity of 25 milliliters of H2SO4 when titrated with 45 milliliters of 0.2 molar NaOH. So the first thing that I'm going to do is write my formula. MAVA is equal to MBVB. Okay, and now I'm going to say I have H2SO4 and I have NaOH. I know this is a neutralization reaction. I know I have a strong acid and a strong base, but what I'm looking at right here is the ratio of hydrogen ions to hydroxide ions. I have 2 hydrogen ions here and 1 hydroxide ion over here. Now, what you have to do here is basically say I have double the amount of hydrogens than I do hydroxide. Don't try to do anything crazy or strange, and don't try to overthink this. If you have 2 hydrogens here and 1 hydroxide here, keep it that way. Let's go back and start plugging in variables. So it says determine the molarity. Okay, I'm looking for a molarity of 25 milliliters of H2SO4. All right, so I am looking for Ma. Ma is my unknown. My volume of my acid is 25 milliliters, so I'm going to change that over to 0.025 liters. And then I'm going to keep on going. When titrated with 45 milliliters of 0.2 molar NaOH. So the molarity of my base is going to be 0.200 molar. The volume of my base is going to be 45 milliliters, which of course I'm going to turn it into liters because molarity times liters gives me moles, and I'm trying to make sure that the moles of both of these sides are equal, like we saw with the previous example with the graph. Go back and look at it if you don't know what I mean. So we need to do 0.045 liters. Now, here's the killer. This is the base side over here. We have NaOH. Again, 1 hydroxide, 1. Here's the acid side, H2SO4. We have 2 hydrogens. Because we have 2 hydrogens that have the ability to ionize, I'm going to multiply this side by 2. So when I do this and I solve for the molarity of my acid, when I solve for Ma, my final answer is going to be 0.18 molar. And I know that I've done this right because if I multiply together 2 times 0.18 times 0.025, that's a sad looking 2, 5. And I multiply those all together, I get 0.009. And if I multiply this molarity times that volume, I get 0.009. So they are equivalent to each other. This is where we'd be at the equivalence point, or stoichiometrically equivalent. Some neutralization reactions involve bases, which can react with more than 1 mole of hydrogen ion in solution. Therefore, the ratio of hydrogen ions and hydroxide ions may not be 1-to-1. As a result, again, the MAVA is equal to MBVB relationship must be adjusted based on the given chemical species. So let's look at this example. Determine the molarity of 150 milliliter solution of SrOH2 when titrated with 0.2 liters of 3 molar HCl. So the first thing that we're going to do is write our formula. MAVA is equal to MBVB, where Ma, the acid that we're looking at here, is HCl, and the base that we're using is SrOH2. Okay, so now this says determine the molarity of 150 milliliter of SrOH2. So the volume of my base is 150 milliliters. So of course we're going to change that over into liters. So 0.15 liters. We are solving for the molarity of my base. My molarity of my acid is 3 molar. The volume of my acid is 0.2 liters. And then again, I'm going to look at the ratio of the hydrogen to hydroxide. This is in a 1:2 ratio, so I'm going to multiply my base side by 2. When I do this, I'm going to multiply 3 times 0.2 and divide that by 0.5 times 2. So the molarity of my base will be 2 molar. And again, we can do a check. 3 times 0.2 is 0.6. And then if we put in the molarity of our base, which is 2, so 2 times 0.15 times 2, this is also 0.6. So again, we can see that they're stoichiometrically equivalent. We are at the equivalence point when we have a molarity of 2 molar for our base. Titrations involving precipitation and redox reactions. Titrations are not limited to acid-base reactions. Titrations can also be used in precipitation and redox reactions. So there are 3 steps that you're going to follow if you're looking at your titration reaction and you can't 100% say to yourself, wow, that's acid and base neutralization. If you look at your reactants involved and you can't 100% verify that, then follow these 3 steps. So the first step you're going to do is, of course, follow my AP Chemistry mantra, which is convert to moles. So convert to moles from a given quantity of one species present in a reaction. Then use a balanced chemical equation to determine the moles of the desired chemical species. So you'll have moles of one species, you're going to find moles of another species. And then once you have the moles of the species that you want, you're going to determine either the molarity or volume of the desired species. So let me show you what I mean. Here's an example. Carbonates in the form of antacid tablets can be used to neutralize stomach acid. 25 milliliters of 0.1 molar sodium carbonate solution completely reacts with 35.3 milliliter hydrochloric acid in such a simulated neutralization. Determine the concentration, molarity, of the acid. Okay, so I'm looking at this and I'm saying sodium carbonate and hydrochloric acid. Yeah, I'm not 100% that this is a strong acid, strong base, MAVA equals MBVB situation. So I'm going to go through steps 1 through 3. And the first step I really should do before anything, more like step 0, is write out a balanced equation, because you're going to need a balanced equation. So sodium carbonate, Na2CO3, reacts with HCl, HCl, great. Okay, so if I look at this, I know that the Na is going to go with the Cl. So Na plus 1, Cl minus 1, that gives me NaCl plus. Now, if I look at my other 2 components coming together, I have H and CO3. And I know H and CO3, and I don't want you to write anything on the line yet, but H plus 1 and CO3 minus 2, you cross those 2 down and you get H2CO3, carbonic acid, which is extremely unstable, and in these types of equations will automatically break down into CO2 and H2O, which I mentioned in a previous video. So as soon as you see hydrogen carbonate, most likely, if you're my student, you're going to break it automatically down into CO2 and H2O. And if you're not my student, then you should inquire with your teacher whether you should keep it as H2CO3 or CO2 plus H2O. For my students, I'm going to say, hey, make it CO2 plus H2O. Fantastic. And then the next step is going to be to balance this thing really quick. So 2 NAs, I need 2 NAs, so those are balanced, great. And then I'm going to go on to my CLs. 2 CLs, I need a 2 in front of here, so my CLs are balanced. 1 carbon, that's all good to go. And then I have 3 oxygens over on this side. 2 plus 1 gives me 3. Perfect, it's balanced. Great. So now I have a balanced equation. So step 1, convert to moles. Well, what do I have to work with to convert to moles? Well, I have 25 milliliters and a 0.1 molar solution of sodium carbonate. So that says molarity formula to me. So step 1, molarity formula. Molarity is equal to moles over liters, and I am going to start plugging things in. So I have 0.100 molar sodium carbonate, Na2CO3 is equal to moles. That is what I'm going to solve for. And I have 25 milliliters, so that is going to be 0.025 liters. And then I am going to cross multiply here, and I am going to get 0.0025 moles of Na2CO3. You need to label. No naked numbers, okay? Moles of Na2CO3. And for the love of all that's good in this world, do not round. Don't do it. Don't round it to the very end. And even then, think deeply about rounding. Okay, so now I have moles. So step 2 now is going back and converting from the moles of substance that you have to the moles of substance that you want. So we're going to say 0.0025 moles of Na2CO3, and I want to get this from moles of Na2CO3, and I want to get it to moles of HCl because I have a volume of HCl and I want molarity, but this is a way that I can get moles. So I'm going to go up here and I'm going to see there's a coefficient of 2 right here, and there's a coefficient of 1 in front of the Na2CO3, and then I'm going to say to myself, moles cancel moles, so 0.0025 times 2 is going to give me 0.005 moles of HCl. So, which is fantastic because now I can do step number 3, which is using the molarity formula again. Molarity is equal to moles over liters. And I want the molarity of my acid, so I want molarity. I have 0.005 moles of HCl with a volume of 35.3 milliliters, which I know is going to be converted over into 0.0353 liters. And, okay, moles over liters, molarity, HCl, that's the acid. So when I divide these two numbers together, I get my final answer of 0.143 molar HCl. And if you stick to this pattern, solve for moles using the molarity formula, used a balanced equation to go mole to mole, and then use the molarity formula again to find the variable that you want, you really can't go wrong unless you screw up the math, and that's a separate topic. Some metals will react vigorously with acids to produce hydrogen gas. Determine the mass. Ooh, this is a little different. Determine the mass of zinc metal that reacts completely with 75 milliliters of 0.2 molar sulfuric acid. Okay, interesting. So we need to have a balanced chemical equation here. So we have mass of zinc metal that reacts completely with sulfuric acid. So Zn metal plus H2SO4 looks like a single replacement reaction to me. What's going to happen? Well, the zinc is going to kick out the hydrogen because zinc is more active, so hydrogen gas by itself. And then we know that Zn is +2 and SO4 is -2, so that's going to give us ZnSO4. And then I'm going to look to see if I have to balance my equation, and guess what? I don't. So step 1, use the molarity formula. Molarity is equal to moles over liters to figure out moles, because I have 75 milliliters of 0.2 molar sulfuric acid. So let's figure out moles of sulfuric acid. So 0.200 molar sulfuric acid, solving for moles, and it's 75 milliliters, so that means 0.075 liters. I'm going to cross multiply, and when I cross multiply, I'm going to get 0.015 moles of H2SO4, because I'm going to label everything. Okay, step 2. What do I need to do with step 2 now? Well, I have moles of H2SO4. What are they really asking for here? Are they asking for a molarity? Are they asking for a volume? Or are they asking for something different? They want the mass. That's grams of zinc. Well, I have moles of H2SO4. I can get to moles of zinc. Sure I can. So 0.015 moles of H2SO4, multiplication sign and a line, moles of H2SO4, and I want moles of zinc. And I could go on to do potentially other things if it was a different scenario, but I only want mass of zinc. So there's an assumed 1 in front of the Zn, and there's an assumed 1 in front of the H2SO4, so 1 and 1. So these two cancel, and I'm in moles of zinc. Do I want to be in moles of zinc? Not really. I want the mass of zinc. So I'm going to put another multiplication sign and a line, and I know for every 1 mole of zinc, the atomic mass of that is going to be 65.4 grams of zinc, because I would look on my periodic table, equals, so moles of zinc cancel moles of zinc, so I'm going to do 0.015 times 1 times 65.4, and I am going to get 0.981 grams of zinc metal. And that is my final answer. So the moral of the story of this example is read the directions carefully, because you never know what you need to solve for. So read, underline, and then read it again. So what did you learn? We went over some basic acid-base titration terminology. We talked generally about equivalence point, endpoint, and indicators, and please know when we get to acid-base equilibrium in the future, we'll address all of that again. We talked about the basics of acid-base titration. We did some worked examples. We talked about precipitation and redox reaction titration, and we did some worked examples with those as well. Need more help? Feel free to contact me. Have a great day.